So next on is John Mason, which I'm sure everyone knows John. John has been involved in astronomy since, how old were you?
7 years old.
So he was 7 years old, was a frequent resident of Sky at Night, and now is very closely involved with a planetarium in Chichester, which I was at actually a couple of months ago, giving a talk there, and it's an absolutely fantastic venue. And I know it's quite a long hike from here, but if you do get a chance to go down there, it's a really impressive planetarium. It uses the projector from Armagh, doesn't it? Which is where Patrick Moore was director for
3
a
years,
while.
65 to 68.
Yeah. So there's a lot of history there, and it's a proper planetarium projector. It's one of those nice Zeiss projectors that looks the part. It's not a kind of digital projector. So I'll hand over to John now, talking about outbursts and meteor streams.
Thank you very much. Well, Nick's already stole almost the first line of my talk because he's absolutely right. Comets are the progeny, if you like, of most meteor showers and streams. You can see in this lovely image by Terry Lovejoy of C2006P1 that wonderful dust tail, and you can see the beautiful structure in there. And one of the key things about when comets released dust is that the dust is released predominantly in the lead up and after perihelion passage, but each orbit of the comet, the dust is released with the orbit of the comet at that time. And so if we look at the situation here, where we have the orbit of the comet in purple and the orbit of the Earth in blue, and this is obviously a comet with a highly inclined orbit, there are vast numbers of comets out there releasing incredible amounts of dust, and we've seen that in some of those wonderful images that Nick showed, but we never ever see that dust as meteors in our atmosphere because the orbit of the comet does not come close enough to the orbit of the Earth. And so we need there to be a relatively close intersection between the Earth's orbit there in blue and the comet's orbit in purple at either the ascending or descending node of the comet's orbit, or in some cases at both nodes. And so we have a subset of all the dust being released by comets into the solar system. We have a subset of that dust that we can actually see as meteor showers. Now, the streams of dust going around all those different comet orbits can be seen as the various showers during the year. And this is a global meteor network graphic showing the major meteor showers of the year. And there are about 30 of them. And you can see there they vary in intensity. And in general, the intensity increases as the Earth goes through the stream and then decreases as the Earth exits the stream. And we can see there that the Geminids are probably the most active stream of the year, followed by the Perseids, and then a number of lesser streams. This is also shown in this lovely graphic from Alex Pratt and William Stewart from the nematode data set. And you can see there in colour the varying major showers of the year. And you can see very clearly the radiant drift. So if we look here at the northern and southern Taurids, have a steady hand with the lever this long, the northern Taurids and the southern Taurids, you can see that as the Earth moves round in its orbit, there's a roughly 1 degree eastwards drift per day. And we can see other major showers of the year, the Perseids, the Quadrantids, the April Lyrids here, and many, many others. Now, those meteor showers, if we go back probably 25, 30 years, I remember most people thinking, well, the major meteor showers of the year, the Perseids, the Geminids, they don't really change much from year to year. But that is just not the case. And as our observations have become more detailed, and particularly with modern video camera monitoring, we have realised that the majority of the meteor streams that we see have variations from year to year. But what I want to talk about are particular variations which may be described as outbursts. Now, I'm going to define an outburst in a meteor shower as a brief, usually few hours, enhancement in the activity of the stream that stands out significantly above the usual random fluctuations in annual activity. Now, all meteoroid streams display fluctuations in activity from year to year, but there are unexpected or predicted outbursts that occur in that activity. And those outbursts have actually been a major factor in improving our understanding of how the dust is laid down in meteoroid streams and the role of those individual dust filaments or dust trails in affecting the activity of the shower. Now, I'm going to talk about 3 different types of outbursts. Now, some meteor streams have a low level of activity year upon year upon year, and then we have a brief period of very high activity, which is usually related to the return of the parent comet. So in the case of 55P Tempel-Tuttle with the Leonids and 21P Giacobini-Zinner with the October Draconids. And in those cases, when the comet returns to perihelion, we will get outbursts in activity, some of which have been very spectacular indeed. However, it is the exception that proves the rule. And there have also been outbursts that have been seen when the parent comet is far from perihelion or indeed far from the Earth. So there are aspects of that we still need to understand. Then there are the showers that we see almost every year with varying levels of activity, but which occasionally display outbursts in that activity superimposed on the baseline annual variation that we see. So, for example, we have the April Lyrids, the June Boonids, even the Perseids, Orionids, Alpha Monocerotids, and so on. Lots of showers where, and I've listed the years there, where there have been outbursts in activity superimposed on the background level that we see every year. And then we have streams which are formed when a comet nucleus disintegrates, breaks up. And Nick's shown a lot of lovely examples of comet nuclei disintegrating. And I remember one night back in 1975, I think it was, observing with Paul Doherty and Patrick Moore, and Paul actually doing a sketch of the breakup of the nucleus of Comet Vest at that time. And it was an amazing thing to see. He was an absolutely great artist, but also a recorder of detail. So most of those comet breakups, the dust stream formed doesn't come near the Earth. And so we do not see the outbursts that those streams cause. With 2 examples, of course, the Andromedids, related to defunct comet Biela, and the Tor Herculids, which I'll talk about later on. The whole aspect of forecasting when outbursts are going to occur goes back to one of those showers I've already mentioned, the Leonids. Now, the Leonids, associated with 55P Tempel-Tuttle, have produced some absolutely incredible outbursts in activity at roughly 33-year intervals. We can see these lovely woodcuts from the 19th century of the great storms of 1833 and 1866. And we had other major activity of that shower leading right the way through the 20th century, until we come to the most recent return of Tempel-Tuttle in 1998. And there were lots of forecasts made, and in my presidential address, I confidently forecast when activity was going to occur. And I was completely wrong. And the reason I was completely wrong is we didn't realize something very important about the way dust is laid down by comets whose orbits we intersect. And that whole aspect of changing our thinking of how the dust was laid down was brought into sharp focus with the Night of the Fireballs, November 1998. Now, on that very night, Martin Mobley and I were up in the Himalayas in Darjeeling with a video system and complete cloud. Now, the story of that escapade has been told brilliantly by Martin in one of his comedic sketches. But I remember Martin looking at the TV screen that night. We had almost completely cloud, and through gaps in the cloud, he was seeing bright flashes. And we thought at the time, is the video system at fault? Or is it really something we were seeing? We didn't know. Until, of course, we realised that if we'd stayed back at home in England, we would have seen the thing perfectly, because the sky was brilliantly clear over most of southern England. And this picture, you can see, taken on that morning, shows this succession of Leonid fireballs occurring almost a day before the predicted peak would occur. Now, we observed the predicted peak, and the rates were much lower and nowhere near as spectacular. And this got people thinking, why is it that we were so wrong? Why did we predict the peak at the time when we went through the nodal passage time for the comet? But why was this some hours, 20-odd hours earlier? What was happening here? And it got people thinking about the way the dust was laid down. And we realised that our idea of how meteor streams are was completely wrong. These are not, I like to think of these sort of thick salami sausages, and you take a slice through it, and it's dense in the middle and it's less dense on the outside, and the Earth travels through this sausage-like cylindrical stream of dust, and the rates increase as you get near the middle, and then they drop again as you go out. That is just not the way it is. Because within that sausage-like envelope, that cylindrical envelope of dust, there are all of these narrow filaments. We could think of them like strings of spaghetti woven through that cylindrical cross-section. And if the Earth happens to pass through one of those thin filaments of dust laid down at different perihelia of the comet, then we will get an increased activity. Now, it was David Asher and Robert McNaught who first got a handle on this dust trail model. And they made predictions for the 1999 return of the Leonids, not based on the time of the nodal crossing, but based on where these filaments were laid down at different apparitions of the parent comet. And you can see that in the early morning hours of November 18 there, the blue dot, November 18.0, just above it is that oval brownie period, 1899. And they predicted almost exactly when the peak of that activity would occur. Now, the whole event was over in just a few hours. And it was only for about an hour or so that we got amazing rays. This is a picture from the Sinai Desert by Nigel Evans, a stack, of course, a composite, but showing all the meteors radiating out that night. And there we can see the rates rising to about 60 meteors per minute at peak. And you can see that the full width half maximum is only just over an hour. So these are very brief, intense events. But the time of the peak was within just a few minutes of what Asher and McNaught had predicted. And we realised that we were really onto something. And by going back and modelling the 1998 apparition, the Night of the Fireballs, we realised that that was from the 1333 dust trail. So we're seeing two filaments of dust laid down hundreds of years apart. One of them, the 1333 dust trail, relatively rich in large dust grains producing those fireballs, and the 1899 dust trail, much more recent, with a lot more smaller grains still in it, giving a rather different pattern of activity. So we learned a couple of things there about the way the dust is distributed and the fact that as a stream gets older, as the filaments get older, so the smaller grains are preferentially lost due to perturbations, things like the Poynting-Robertson, Yarkovsky effects, and so this the older a filament becomes, the relatively more rich it is in larger grains. And so you, depending on the type of filament you're crossing, how old it is, the magnitude of the meteoroids you see and the meteors you see will change. So, what does this mean for 2025? Well, now, after Asher and McNaught, there are a large number of people who are making predictions about these. Vaubayon, Maslow, Sato, Watanabe, lots of people who are doing computer models. And if you look at this year's Leonids, this November, conditions are very, very good, no interference by moonlight. You can see that there are 6 basic ideas of trails that we're going across. Now, the normal nodal crossing is about 18 hours on November 17. But there are other filaments that we are due to cross at different times, and you can see them listed there. But we don't know what sort of rates they'll give. Will they give any noticeable enhancement at all? Will they be relatively rich in faint meteors, richer in bright meteors? We just don't know. The only way is to go out and observe to find out. We're only going to refine these models and perfect these models by observation. 2026, the moon is just past first quarter, again reasonably favourable, and again there are a lot of predictions for different trails going back. You can see there we've got the 1533 trail, and then more recent trails, 1800 trail, 1699, 1600 trail, all predictions in different models by the different people who are doing this work. So there's a lot of possibilities for looking at the activity of these trails over time. So moving on now to the Draconids, connected with 21P Jacobi Zinner, this has produced some of the most spectacular meteor storms of the 20th century, particularly 1933 and 1946. And we can see here in this model by Vaubayon, you can see the Earth's path, the diagonal line going from bottom to top, passing through those dust filaments ejected from this short period comet in those years there, and again giving very, very high activity indeed. Now the Draconids, the October Draconids, peak this Wednesday. Not particularly good because the moon is going to be pretty bright this week. However, nonetheless, there are a number of forecasts about what might occur. And you can see there that there are some various predictions of activity between about 1500 and 1600 UT this coming Wednesday. But the likelihood is that these particles will be, these dust grains will be of very low mass, less than 0.01 of a gram, and travelling at the slow geocentric velocity of the Draconids. And we can see that they're going to be magnitude +4 or fainter. So a challenge even for video observers, but not for observers doing radio work. And I want to show this example from Nick Quinn of radio observations of the Draconids, as you can see, back in 2011. There was a fairly small outburst in Draconid activity very early in the evening when the radiant wasn't well positioned for visual observers, but you can see his observations in blue and yellow show the activity the day before and after, and the activity in red clearly shows the peak. So I want to encourage observers who have the equipment to look in radio to try and make observations like this. It'll be in the late afternoon of this Wednesday. It doesn't matter if it's a storm, if it's cloud, if it's bright moon, the radio observations may pick this out. So this is an opportunity for radio observers, and again, the Draconids are certainly a shout to watch. But even some of our more regular showers, like the Perseids in August. And there is another one of those lovely drawings that Nick mentioned that were done, this one by Thomas William Webb back in 1862, of the parent comet of the Perseids, 109P Swift-Tuttle. And you can see those lovely structures that they showed, which, as Nick has shown, do bear relation and to what's actually going on in the comet. Now, when Swift-Tuttle came back in 1862, and again in 1992, there were major peaks in activity. And you can see that the ZHR in, for example, 1862, 1863 was certainly several hundred meteors per hour. And in the early 90s, we had very, very good coverage, 91, 92, 93, around the time of the parent comet's perihelion, with rates being several hundred meteors per hour. But since then, in more recent years, we have had other outbursts in Perseid activity. There was a nice one in 2009. There was another one, as you can see there by the blue curve, 2016. Now, the normal Perseid peak is the lower little bump there on the defining line, and this is the outburst. You can see it's occurring some way before the normal Perseid peak. And in fact, in recent years, there has been a pattern that there has been enhanced activity between 0.7 and 1.5 days after the main maximum. The main peak is well established, but Mikhail Maslov's modelling has shown that one of the reasons Perseid rates have been lower in the last few years is because we haven't been going through a dense area of the stream, and that from 2027, Perseid rates will go up again to about 100 meteors per hour at peak from the current 60 to 70 when we go through a part of the stream disturbed by Jupiter's perturbations. Vauban's calculations indicate an enhancement there, as you can see on August the 12th in the late afternoon. Another one you can see around the early morning hours of August 13. Why is this important? Because on August the 12th, 2026, there is going to be a total eclipse of the sun. And that means it must be new moon. And that's good news for meteor observers. So I've got a couple of hundred people watching the eclipse with me. They also are going to be out late that night watching the Perseids. So it's hopefully going to be a good night for the Perseids immediately after the total eclipse. And maybe radio observers earlier that day might get that extra little peak predicted by Vauban from the 1079 dust trail, although it's a very old trail, so there may be very low rates. And another filament there shortly after the main peak. So even with the Perseids, there is things to watch. A shower that not many people maybe have heard of could well be on the map in 2026, the September Epsilon Perseids. There's 3 possible encounters with trails on September the 10th, 2026. We don't know the parent comet. So the modelling has been done a bit on the fly, on the base of a number of assumptions which may be wrong. But it's worth looking to see whether we can detect anything in the early hours or early morning of September the 10th. Again, it's going to be something that radio observers will pick up, but also video observers in the early morning hours that day. And it's always worth looking to see whether anything might occur. So September Epsilon Perseids, September the 10th, 2026. Now, the breakup of comets. Here we've got 73P, Schwarzmann-Volkmann 3, breaking up in April 2006. And after that comet's breakup, some years after, we had a spectacular outburst of the Tau Herculids, which are connected with that comet. So again, we have, if you like, generated a new shower, new outbursts from the breakup of a comet. But the most famous example, of course, is Comet 3D Biela, which broke up in 1846. The nucleus split into 2. The 2 parts came back again and were never seen. But afterwards, in 1872 and again in 1885, there were great meteor storms coming from the constellation of Andromeda. And here we can see the peaks are heading up for 10,000 meteors per hour, but again, very, very short in their activity. And modelling of the dust trails from these showers have shown, and you can see here, that in 1872, on the left there, we go through the trails from 1839 and 1846. Very, very fresh trails generated by the breakup of the comet and leading to that meteor storm. And we can see that in 1885, again, we go through the 1846 and 1852 showers of dust. We thought the Andromedids had gone, but they're not. They came back in 2011, and you can see here some modelling done by Paul Wiegert and his team, and you can see here the Earth's orbit, the curved line right to left, and the various dust trails, particularly 1649 and 1758. And it looks like the outburst in 2011 and another one in 2008 were primarily dust from the 1649 return of the comet. So Wiegert and his team then produced a whole series of predictions, one of which was the return of November 2023. It didn't happen. I gave a talk at the BA meeting with Nick talking about what was going to happen. Nothing happened. That is actually very, very useful, because you can then go back and say, why did we get it wrong? What in our model needs tweaking? And this is the value of observing these outbursts that we can tweak the model. And when the model was tweaked, guess what? There wasn't going to be an outburst in 2023 after all. So this is how we can refine these things. And let me finish with a summary of why the observations of these outbursts in meteorite streams are important. They enable us to refine the positions of particular dust filaments within the stream. They enable us to establish the activity levels of the various dust filaments within the stream, to determine the size distribution of the dust grains within the stream laid down at different epochs. And for that, we need observations in radio, video, visual, photographic work to look at the whole size range of dust grains. Because remember, the older the filament, the more of the small grains will be lost, and the greater the preponderance of the larger grains. But we can look at these effects and their effect on the different filaments laid down at different times. And finally, we can improve the accuracy of dust filament modelling for future returns of the shower. And it's now 10:45 and time for me to stop. So like Nick, I'll be happy to take questions in the tea break, which I believe is now.
I think we've got half an hour coffee break, so I think there is enough time. If anyone's got any questions, we'll take 5 minutes for questions now. If not, we'll go straight to the coffee. If you wait for me to bring the microphone.
Nick's going to bring the microphone over.
That's fascinating, John. That was amazing, right? What really amazing to me, I've never seen this talk before, that how is it you can find out you've got meteors from 1633 and all these 1033 or whatever? So
because with modern supercomputers, you can take the orbit of the comet as we know it, from observations made of the comet, from astrometric measurements made showing its position, we know the orbit. We can then, knowing the positions of all the planets and their likely effect, planetary perturbations, we can run those commuter models backwards in time to look at what was the orbit of the comet at a particular future apparition. And we can go way back, hundreds of years. Now, the accuracy decreases as we go back in time if we don't have observations to refine it. So historic observations of many of these comets is very important because it enables us to establish the orbital parameters at that time. We can then refine our computer model as we go back and then go back a bit further where we may not have any observations. So those models rely on astrometric data now, astrometric data from past apparitions as far back as we can go, and the sophistication of the computer models in turn.
got any questions?
There's one over here.
Thank you. Not a question so much as a comment, because you mentioned eclipses and meteors. In 1999, having waited 33 years, I saw the total eclipse, not from England, the last place I wanted to be, in view of the English weather in the middle of August, and I was right. So I was in Romania, Râmnicu Vâlcea. And in my video of the eclipse, which was on August the 11th, the height of the Perseids, you could actually see 2 Perseid meteors crossing the disk hidden by the moon.
Well, I'd be very interested to see that, certainly. I must admit, I wasn't aware that anyone had done that. Certainly, I don't know whether next year, at the peak of the Perseids, we'll see anything. It seems unlikely because the Perseid radiant won't be above the horizon, so it seems unlikely. But I'd certainly be interested to see the video and see the trails on it.
It was shown on Romanian
Râmnicu
TV.
Vâlcea, that's where it was the greatest duration,
that's
that
right.
eclipse. Yeah, that's right.
Very good. So, Jonathan, did you just have a quick...
Nick has got... Oh, yeah, Nick has got one at the back, so...
Well, they're putting out the tea anyway.
Sorry, well, quick one. One for both of you, actually. I think I've read that the Comet Lemon is likely to cross Earth's orbit on the 3rd of October. Assuming it does have, you know...
It's a different comet.
Okay, sorry, the other comet.
Yeah.
R2?
Yeah.
Right, okay. Assuming it has some dust, what are the prospects for a meteor shower from that comet, and how long would we need to take to see it?
So there is a bit of a problem. So yeah, that comet, we do cross close to the orbit, I think within about 7 million kilometres, but the radiant's about 2 degrees from the sun. So we aren't going to see it because it'll be daytime, but it might be radio observers.
Again, it might be radio.
Oh, maybe, possibly. I mean, the other thing is about the period of that comet, we don't really know how much dust there is likely to be in its orbit. But yeah, it's a possible.
There are always going to be showers for which we have no parent comet known, where over time we might establish what the parent comet is, and there will be new showers being generated by more comets coming in. But the crucial thing is that the Earth's orbit has got to go close to the obviously descending node of the comet. Has got to be within a certain distance for us to see any meteors from that comet.
And that particular comet has another nodal crossing in April, which is
next April, is that?
Perhaps more favourable. However, the mist distance is similar, so unlikely to see any activity.
Is it 7 million, did you say?
It's 0.04 AU, so...
Oh, it's long.
So
it's high.
It's not in the sort of 0.001.
It's not in the ballpark we want,
so
is
it's not really close enough. But you never know. Jupiter perturbations could have done anything. However, my comment was more associated with what Nick was saying about Starlink satellites. And we're very aware that astronomers suffer from light pollution and are starting to team up with environmentalists to combat light pollution. It may well be that astronomers need to team up with atmospheric scientists to combat Starlink satellites, because there's an awful lot of launches, but there's also an awful lot of re-entries, and they are generating aluminium oxide dust in the upper atmosphere, which may possibly interact with the ozone layer and destroy it.
Yeah.
So that's horizon scanning,
A subject
but it
very
is a
dear to
hot
your heart
It
too.
is a hot topic.
Absolutely, yeah, very important.
Yeah, thanks, Jonathan, for raising that. I've seen that mentioned several times now, and it does definitely seem to be a real issue. So, Dennis looks like he's got a really burning question. We really need to move to the coffee break, but there you go.
John, most of your talk, well, all of your talk was about meteor streams, but you don't mention anything about sporadics. Now, those are the most meteors that we see, so where are the sporadics?
The sporadic background is generated by the slow dissolution of all of those streams into the background. And there is a sporadic activity all the time as a background level. If you remember when I showed Nick Quinn's radio results, he'd very well got the background rate which would be sporadics and maybe very many minor showers with the peak of the draconid shown. So yes, there is. I didn't mention sporadics specifically because the talk wasn't on that subject. But the fact is, yes, there is a sporadic background, and occasionally in that sporadic background we will get a sudden outburst in activity. Now, we may not have any idea where that's come from. We may not know if it's connected with a periodic comet or not. And over time, knowing the nodal crossing point, we might be able to work out whether it's connected with a known periodic comet or not. But outbursts do occur sometimes when we don't expect them out of the sporadic background. But the sporadic background is generated by this dispersion, planetary perturbations, pulling material out of stream. And there is this general background level of activity all year round. Peaking September, lowest February, March, to do with the apex of the Earth's way, the direction the Earth's moving in space. But sporadic rates do vary during the year slightly. But yeah, it's there all the time.
I don't know whether it's dark enough at Tarbert Nest for you to see the zodiacal light, but that's essentially all that dust laid down in the
very smallest grains in the...
Anyhow, we better take a break for coffee now. Plan is to resume at 11:15 with Jonathan's talk on 50 years of comet observing. Thank you, John.